A curve has parametric equations x equals 2 cot t, y equals 2 sine squared t, where t is between 0 and pi over 2. Part A finds an expression for dy by dx in terms of the parameter t. So I'm differentiating y with respect to x with parametric equations. I know that that means that I can do dy by dt divided by dx by dt. That's my formula for differentiating parametric equations. So let's do that then. Let's work that out. Let's differentiate y with respect to t. So if y is 2 sine squared t, to help me differentiate that, I'm going to think of it as 2 sine t all squared. Means the same thing. So to differentiate that, I'm going to times by the power. So I'll get 4 sine t. The new power would be 1. Then by the chain rule, I have to multiply that by the derivative of the inside function. The derivative of sine is cos. So this is my dy by dt. X is 2 cot t. To differentiate that, well, actually, we do get given this in the formula booklet. The derivative of cot is minus cosec squared. So here, this is going to be minus 2 cosec squared t. And so this is going to get substituted in here. So let's simplify that. My dy by dx is equal to 4 sine t cos t divided by minus 2 cosec squared t. And for part A of the question, it doesn't actually say how to write my answer. It just says leave it in terms of pi. So in theory, you could leave it like that. But I can see some very obvious simplifications to do here. And I think the simplifications are probably going to help me for part B of the question. The obvious simplifications I'm talking about is, first of all, the 4 divided by the minus 2 is minus 2. So I can rewrite it like this. The second simplification I'm thinking about is cosec squared. Well, cosec is 1 over sine. So cosec squared is 1 over sine squared. So if I'm dividing by 1 over sine squared, I can think of that as multiplying by sine squared. Which would simplify to be minus 2 sine cubed t cos t. Like I say, I didn't necessarily have to do these steps here, but I think it's going to help me for part B of the question. Talking of part B says to find an equation of the tangents to the curve at the point where t is pi over 4. So, t is pi over 4. That's going to allow me to work out the gradient now. I worked out the gradient function in part A of the question. It's being minus 2 sine cubed t cos t. So when t is pi over 4, the gradient of the curve then will be minus 2 times sine pi over 4 cubed times cos pi over 4. Which, if I type that into my calculator, so sine pi over 4 is root 2 over 2. And I'm going to cube that, multiplied by cos pi over 4. So I work out that the gradient of the curve at the point when t is pi over 4 is minus 1/2. Which means that the gradient of the tangent is going to be minus 1/2. By the way, if I hadn't done this simplification here, the substituting the pi over 4 into this expression here would probably have been quite difficult for you. That's why it's a good idea, if you can, to simplify things as much as you possibly can. Anyway, we've got our y equals mx plus c. I need to know a coordinate that this curve goes through so that I can work out my c. Well, I know that when t is, let me just create a bit more space, when t is pi over 4, that's the point where I'm trying to work out the tangent. So if I use pi over 4 with the parametric equations that I was given at the beginning, that's going to tell me the y coordinate and the x coordinates when t is pi over 4. I can then use that to work out my c. So when t equals pi over 4, x is equal to 2 cot pi over 4, which is the same thing as 2 over tan pi over 4. Tan pi over 4 is 1, so 2 over 1 is 2. Now substitute the pi over 4 into the y equation. Sine pi over 4 is root 2 over 2. So root 2 over 2, root 2 over 2 squared is going to be a half times by 2 is 1. So when t is pi over 4, we have the coordinate 2, 1. If I substitute that into my equation then, so 1 equals minus a half times 2 plus c. So I find that c is going to be 2. Therefore, the equation of my tangent is minus a half x plus 2. It doesn't say what form I need to leave my answer in, so I'm going to leave it like that.